Okay, hi everyone. Thanks for making it here early this morning. So today's a great day for me because I get to talk for 3 hours about maths, which I love, and I hope it's a good day for you as well. So remember last time we said that we want to kind of port over everything we did about flat connections into this p-adic analytic world, but we saw that there was this problem about infinite dimensionality already of kind of the analogous Durand cohomology group or equivalently extensions of flat connections, even just over A1. And I said that the solution was something called overconvergence. So maybe let's just recall the setup that I'm going to be working in all the time is going to be, we're going to have y inside X is going to be an open immersion varieties of FP. And then we had some p-adic formal scheme X and a closed immersion X hat. So definitely you can just, it's useful in the theory to have this in quite broad generality, but you can just think that what we have is we have a lift of X to a variety of a ZP. And then this is that thing I described last time. So this is formal completion along special fiber. Okay, and so we need this language because we're interested maybe in working with some kind of category of connections on Y, or rather on the tube of Y. And we want to say that it overconverges, but we need to say where it's overconverging, and it's going to overconverge in the tube of X. So for Y, X, and frac X as above. Strict neighborhood of X. So maybe let's call, remember, technically when we take a tube, we should specify this of X, of Y in X. Tube of X is the general kind of rigid analytic definition, and I'll tell you just in coordinates what it is. Admissible open U containing, well, actually it's already containing the condition, such that if I take U and I take the tube of the complement of Y and X, I want this to be an admissible cover. So this is a definition in general language of the G topology on rigid analytic spaces. But let me make this more concrete. So this word overconvergence is slightly overconverging. So there's this, so if I just took the tube of Y and the tube of X minus Y, then that would also be a cover of, admissible cover of the tube of X. That would be a cover, but it wouldn't be admissible. But rather than think about that, the example you should think of is suppose that Y is D of F bar, so it's the open where some function F doesn't vanish on X, then the tube of Y, remember we said last time was, so F bar is in OX, and then F is in, so lift of it to bracket. And this is the set of points where F is equal to 1. And actually a basis of sorry, the basis isn't quite the right term. So technically it's a cofinal system, but the so an example of an admissible open would be to take the set of all f being greater than or equal to 1 minus epsilon for some epsilon greater than 0. So it's a strict neighborhood. And yes, basically these are the only strict neighborhoods that you ever actually need to think about. So we say that, maybe I'll give a kind of meta definition. This is really, I'm not quite sure I know how to use that word, but so this is a definition which you can apply in lots of different contexts, is what I mean. So a thing on Y is overconvergent if it comes from a thing on a strict neighborhood, on some strict neighborhood. We don't care which one, just that there exists a strict neighborhood. Y in X. E.g., thing could be a function, or it could be a differential. Or it could be a vector bundle with connection. Or it could be a map between map, say maybe Y1 to Y2. So let's give an important example of something which is overconvergent, which came up in Jennifer's talk. So the Kedlaya lift of Frobenius on y squared equals f of x. So remember, this was some function which was meant to lift the function y goes to y to the p. And it had this formula. It was called like phi of y is equal to y to the p. And then you took 1 minus p times h of x over y to the 2p to the half, where h of x is some. This is in zp of x. And this will be something in zp of x. And then you just remember we formally expanded, or Jennifer in her lectures explained how you could formally expand this power series to find the square root. And well, this has convergence properties clearly when y is small. So this but it converges on so a priori it's just defined on the tube where you delete the Weierstrass points, which is exactly the points where the absolute value of y is equal to 1. So I'm kind of not thinking here about infinity, you kind of deal with that separately. But actually it converges whenever y is greater than, see if I can do this, something like e to the minus 1 over 2p, I think. That's right, me. So it's an overconvergent function. Y, where y equals x minus the set of Weierstrass points. This is, I guess, is over fp. Size. Okay, so now I can define the category of connections we work with. First of all, maybe I should just say what the definition I need to say, this definition. So we're going to have y, I'm going to kind of always refer to this y, x in brackets. The trivial isocrystal on, speaking for now, we should call it on y, x. X is one. And sometimes we'll also say that direct sums of those are trivial or constant. So then unipotent, overconvergent isocrystal on y, x. X is a flat connection. The nabla on y such that V nabla is unipotent. So that means that it's an iterated extension of trivial connections, i.e. Has a filtration by subconnections. So I use this here, such that for all I guess I never really said this, but flat connections form an abelian category. So you can speak about a subconnection and you can form a quotient connection. So being trivial is just being an iterated extension of, being unipotent is being an iterated extension of constant connections. So what's the overconvergent? Such that there exists unipotent connection, strict neighborhood U of y and the unipotent connection W for prime on U such that, so basically we want this connection to come from a strict neighborhood such that maybe let's call this inclusion J. This isomorphic. Pull back off. So, I'll give an example. But maybe for this example, let's just to take care of the condition of the connection being flat. Let's take let's take these to be curves. And then maybe this one as well. Then let's take some differentials. Lie on U for U some strict neighborhood of the tube of Y. Then this connection we discussed last time is kind of, in a way, a kind of prototypical example of a unipotent. Let's call it a UOP. So UOI. And so going back to this example of the Cadlai ellipse of Frobenius, one of the reasons that it's very important to have this overconvergent Frobenius for us is that it means that when we pull back, so say any overconvergent connection by this overconvergent Frobenius, we'll get another one. Yeah. Oh, have I got it the wrong way around? So J, so J is going from Y to U. And I have something on U and then I pull it back by J. So yeah, maybe actually, I mean, this is a good point because I meant to draw a picture of a strict neighborhood and I forgot. So so for example, we said that we deleted the Weierstrass disks. So maybe those are disks like this one. And then so these are the Weierstrass disks. So these are the points where Y is less than 1. So these exactly these open balls, like we considered, and the complement of these open balls is a priori, is a nice affinoid variety. But to do analysis, we actually don't want to work with the complement of these balls, but we want to find some smaller disk in those, and we want to be able to extend. So instead of working on this thing here is say Y, and our strict neighborhood is something which shows a slightly eye-watering color combination, like this. Of each of them, yes, yeah, and that's important even in this case of the Cadlai ellipse of Frobenius, because you can define it on a slightly larger strict neighborhood, but the domain in the target could be different. So yeah, and then if you want to have two different spaces, then you have to. So why? I mean, this isn't assuming that Y1 and Y2 are both inside some ambient space. Yeah, these are inside. Okay, so some examples in a second, but before I do, I think I should just make a remark, just for the sake of honesty and completeness. I've told you what a unipotent overconvergent isocrystal is, but I haven't told you what an overconvergent isocrystal is. So it turns out it's not just the definition you might make where you just get rid of the unipotent bit. So there's another subtlety which you need to add, which is slightly complicated to explain, but I'll just maybe say a couple of words about it because this is such a fundamental notion. So I've been discussing a connection as a map. Probably the easiest way to describe it is a map like this. So in exercise, you could dualize this and then think of this as think of this as a map from the tangent bundle of x over k to the bundle of endomorphisms. So what's this gadget? So locally, remember, is isomorphic to R to the n, where you have some affine neighborhood spec R. And so then locally end V is just isomorphic to n by n matrices over R. So it's internal Hom from V to itself. Okay, so the nice thing about this perspective, well, actually lots of things are nice about this perspective. For example, the flatness condition, which maybe seemed a bit arbitrary, you can also express in terms of the fact that both of these objects have Lie brackets. So n by n matrices have a naturally defined Lie bracket, and vector fields, which is what sections of this are, have a Lie bracket. And saying that a connection is flat is just saying that this is a morphism of the algebras. That's just an aside, but so the overconvergence is related to some kind of p-adic convergence of iterating this. So maybe let's call this let's just call it psi. So you can come up with connections on which come from some strict neighborhood of Y, which don't satisfy this convergence condition, and they behave very differently from the things we're going to talk about. But yeah, but because it turns out in the unipotent world, this isn't an issue, so we can ignore it. Okay, so some examples of UOPs. Well, so here's it's a very important example, but maybe it seems a bit silly. We could take any x, and then we could take, say, some point x in xfp, and then we could take our triple to be the point 0, 0, and then x hat. So this is an example where we're not actually taking the last term to actually be the completion of a lift of this one here. So then actually you'll notice that because y is equal to x, there's no overconvergence condition. We're just talking about connections on the tube of 0 inside the genetic fiber of this, sorry, which is the same as, say, if x is a curve. This is the same as, remember, sorry, 0, this should be the point x. Sorry about that. This open ball of radius 1. And so then every UOP on x brackets is trivial. So actually, this is something that we've actually already seen, and we've used this. This kind of just reduces to what we did earlier, just when we saw how you could integrate a differential on a residue. That's actually what this reduces to. So remember, we defined being a unipotent thing by having this filtration of degree n. We can prove this by induction on n, which was length of unipotent filtration. remember what my notation was, but yeah, I guess if n equals 1, then it should trivial to begin with. So now suppose we've got our filtration as above, as over there, like v nabla equals v naught nabla naught inside the dot. Then what are we actually trying to do? So then we can, let's see what's the best way around to do this. I guess we could do it either way. We could just trivialize. So then by induction, we can imply that V1 nabla 1 is trivial. O to the n minus 1. D. So then actually what we're trying to do is that, so that implies that V nabla defines a class in X1 of, well, in this case, actually, we can just work with, we can forget about the overconvergence because Y is equal to X. Category of vector bundles with connection on this E01 minus of the trivial object by n minus 1 copies of it, which is equal to just minus 1 copies of X1. And then we already saw, how do we describe this? This is like a de Rham cohomology group. So this is equal to this is just functions, sorry, differentials of functions modulo. Sorry, this is differentials modulo differentials of functions, or equivalently, it's all the functions you can't integrate. But we saw that if f equals some ai x to the I is in this thing here, then we can integrate it. So that implies this is equal to 0. So that wasn't really an overconvergent example. Does that example make sense? Yeah. Yes. So I mean, I just did a curve just so it was a ball, you know, just because it was one ball. But yeah, if a high dimensional variety would be a d-dimensional ball, and then it would just, well, then x1 would actually just be ends up being just d tuples of x1s on a one-dimensional ball. Also, I guess, yeah, I mean, so the thing that would be different in the d-dimensional case is just the fact that this wouldn't be how you describe the first de Rham cohomology group, because you want to take the kernel of this into omega 2, but everything else is the same. So now let's kind of test that things actually have improved when we've introduced overconvergence. So let's do another example. We could take yx for x to be equal to a1fp, p1fp, and then the formal completion 1zp along the special fiber. So remember, this was the one where when we took A1 FP and A1 FP, so we didn't introduce overconvergence, we got an infinite dimensional X group. So maybe just for yeah, so I guess it's the same statement. So the proof. So it's, I mean, the same argument as we did in the last case. It implies we reduce to integrating F, where F, remember now, is an overconvergent function. So F is an element of OU for some strict neighborhood U. And I told you that we can just think of U as being these things of the form the absolute value of F is at least 1 minus epsilon. So that means that F equals some AIT to the I such that AI times 1 minus epsilon to the I tends to 0, some epsilon. Then you can check that this is basically the kind of exactly why we want overconvergence, that satisfies this tends to 0 epsilon prime for all whenever we make epsilon just even arbitrarily smaller. And that's just because the absolute value, the p-adic valuation of n is kind of unbounded, but it's growing very small. It's growing logarithmically. So when we integrate a function on our strict neighborhood U, we get a new strict neighborhood, but we still have an overconvergent function. So let's say that. Maybe I'll just write that. We have a slightly smaller, and that's exactly kind of the picture to have in mind. Okay. Okay, so we've now defined this category. So let's call it isolager YXP. Sorry, YX. UOPs on YX. And Berthelot in a kind of series of works, some of which were also written up, and I don't know, possibly further strengthened by Lustum, kind of showed that this category enjoys. Oh yeah, sure. E. Oh, sorry, I don't know why I keep doing that. Thanks. Yeah, I see this. Thank you. And so in the unipotent context, this was also further studied by Pierre. Yes, together with Lustum. They kind of showed lots of very nice properties of this. So in particular, I mean, the property that Berthelot showed is that its category, which a priori depends on frac x, is actually functorial in y inside x in some sense. So it actually doesn't depend on your choice of lift of x to frac x. And in particular, I mean, the lift of x, may not even exist, might only exist locally, but somehow this functoriality property means that you only need it to exist locally. So that's an abstract result, but let's use a concrete version of it, which is convenient for computations. So the main reason that we're going to like the fact that, there are lots of wonderful things about this, but for what we're going to talk about today, what matters is that have a lift of, I guess we say we have an action of Frobenius on this category. Right, because I said it's kind of actually just functorial in these schemes over XP, well, schemes over, over FP, well, schemes over FP have this action of absolute Frobenius. And then because it's functorial just in that, then actually that gives us an action. And then, the kind of general argument for that is really beautiful, but maybe what's kind of at the heart of it is an explicit computation which was done earlier by Monsky and Waschnitzer, which is to do with the existence of overconvergent lifts of morphisms locally. The explicit definition is that we just choose some overconvergent lift, which to simplify or abuse notation, I'm also just going to call phi. This is on the tube, so this is now where we fix some x. Actually, maybe let's call, but now let's distinguish it by pulling back. So I'll give some examples in a second. So we're now actually ready to define common integration and common functions. Maybe from now on, we're going to take y inside x, where x is proper. Yes. So, so this particular map explicitly depends on the lift, just because if you have two different lifts, then by definition, they give you different vector bundles with connections. So when I say it's, that's one of the difficult things in the theories. You have to say what it means about being, just depending on the special fiber. And so it's that you have compatible equivalences. That's the idea. And the exact kind of way that you formulate that is very nice. But for example, it just means if you have two different lifts of Frobenius, then you have some kind of canonical isomorphism between the connections you get when you pull them back. We're going to assume that x is proper. And so we want to define these common functions. And remember, by what I just said, if we have an element of this thing, and say we have some FP point of y, and when we pull back by along the tube to the tube of x, by the previous lemma, this will give us a trivial isocrystal. So in particular, we have a full basis of horizontal sections. So let's say that dimension over QP of, just to remind ourselves of the notation, this is sections of V on the tube of X, and then we ask that they're horizontal, which we wrote like this. We have a full basis of sections, which is saying that the dimension of this is equal to the rank of this vector bundle. So concretely, that means, for example, we can compute iterated integrals because we saw that these unipotent connections are the things which give us iterated integrals. And we want to extend these horizontal sections. So if we have X, Y in X, sorry, in YFP distinct, SX in, so we want to kind of analytically continue to some SY. That will define our integration theory, you could say. So this was done by Coleman, and I'm going to describe a formulation of it, which is maybe more due to better reformulating Coleman's results. So with notation as before, there exists a unique collection of isomorphisms should we call it? Let's call them I, X, Y. We could also call it I, X, Y, depending on the enablers from the horizontal sections on X to the horizontal sections on Y. For each, so this is for all the enabler. So when I say it's a collection, I mean it's collection for all of these. Such that, so it has to satisfy three properties. So I want it to be, well, maybe this kind of just to kind of make sure we don't do something silly, that when we take the constant isocrystal, then it sends 1 to 1. So what should, I mean, how should we analytically continue the constant connection? We just send the constant connection to take the you know, this local horizontal section. Let's do a global horizontal section, and we just take that one. So the second one is that it should be functorial so you can call this IXY the analytic continuation, and yeah. No, so this is exactly the substitute, because it's, I mean, this is the pre-image of an FP point. So so I mean, if we're just thinking about the QP points, then this is like a disjoint union. Yeah. Yeah. So I mean, that's the, I think to some extent that's the appeal from, maybe it was the appeal from Coleman's perspective of calling it analytic continuation, because it's a nonsense concept to analytically continue because they're disjoint. But he actually kind of made sense of it. Yes, so I guess it's so it's really just extend just means a map from this to this. But I'm thinking of it extending because I'm thinking if I have a horizontal section, which is basically a kind of, like I said, like an integral, then how do I extend that integral to this? And then in the language of connections, that's saying, how do I define an isomorphism, parallel transport isomorphism from section to here? So I'll give some examples and see that we'll see that it actually kind of comes back to this notion of extending integrals, which Jennifer taught. And then the last condition is the so-called kind of analytic continuation along Frobenius condition. So it looks a little bit funny when you first see it, but I'll try and explain it a bit more with some examples. So it's to do with what happens when you pull back by Frobenius. And the formula, if I haven't messed it up, is pull back by Frobenius. So suppose I've got some V nabla here. Suppose I've got some, let's say for all Sx in Vx nabla equals 0. So I can pull back the section. I'll say what that means in a second. And I want this to be equal to so I think to really, that's the end of the theorem. And well, I guess we'll say something about the proof later, but I won't say too much about it. So this is, I mean, I don't know, I find when you look at these formulas, they're slightly kind of like dazzling. You slightly get lost in the headlights a bit. So let's just unpack what the definition is. There's three appearances of phi star here. So what is phi star? I mean, in general, what is F star if you have a map between spaces? So I mean, these two phi stars are acting on some sections. Well, first of all, what's phi star actually acting on the vector bundle? So recall that locally, I mean, if you have a map, for example, let's just think of the scheme case. If you have a map of schemes X to Y, then you have some a Y module M, and you can pull back M. And if this is given by spec R and this is given by spec S, and then so this is given by some map R to S, and this is some R module, you get an S module just by taking M tensor. Tensor over R with S. Okay, that might seem like I've started a bit too early to get all the way to here, but bear with me. So now, I mean, what do the fibers of a pullback of a vector bundle look like? So recall if we have some Z. So now let's just go back to phi. Z and Y UP. So what does the pullback of the pullback? So what does the fiber of the pullback look like? I mean, for example, from this definition or otherwise, you can see that this is actually just kind of naturally identified with pulling back your original vector bundle at the point phi of Z. So, I mean, what's a diagram to kind of have in mind is that we have our map Y to Y. And then we have a point Z, which is just a map. And then our lift of phi, and these commute, and that's kind of, these are equal. So with that in mind, we can interpret this phi star of so given, say, it doesn't even have to be horizontal. So suppose we're given some section of our original V, then phi star of S, by definition, is just the map which sends Z to S of phi of Z. Maybe I'll just make a couple more definitions and then we'll give an example. So a Coleman section is a tuple. So for all X and FP, we want to have some sorry, this is YFP. Have some local horizontal section. And then we want them to agree to be compatible under this parallel transport map from the Besser-Coleman theorem. Now that's it. So really, I mean, I feel like I'm contractually obligated to actually tell you what a Coleman function is. So to get a Coleman function out of a Coleman section, you just choose a map of vector bundles. So so absolutely, I mean, it's very important actually to get interesting maps that we really don't want this to be compatible with the connection. And so let's say we get a function of y UP by sending y to so I take my section, so let's say y is in the tube of x, so maybe let's say z is in the tube of x, to Sx of z, which is a section, and then I apply f to that. It's now a number. So I mean, how should you think about this? If you remember when we defined what the iterated integral was, maybe I'll just remark. In the formal or in the kind of complex setting, we had this rank n+1 vector bundle with connection, and then we said that this was what you got when you took a horizontal section and took the n+1 coefficient, or the n+1 term of horizontal section written as a tuple. So this was exactly taking a function like f, where it's now +1. The function is +1 coefficient. So that would be the example to bear in mind. Okay. Yeah. Oh, you mean that it's a lift? Yes. Sorry. Yeah. Absolutely. Sorry. Yeah. I should have said that. So yes. Yeah. So phi is now. I see. Yes. Sorry. I think I introduced phi till the here, but then ever since then it just became phi. So yeah, so phi is now an overconvergent elliptic beam. I'll actually write that. That's very important. And the kind of surprising thing is that actually the definition of the integral doesn't depend on the choice of lift. Well, the definition does, but the integral that you get doesn't depend on the choice of lift. Even though it seems to be coming up in all the formulas. Yeah, so let's write that. So important is that phi is some overconvergent lift of Frobenius to the tube of y. Okay, so maybe let's describe the relation to this previous notion of Coleman integration, which came up in other courses. So if suppose we have some one form omega in omega x, for example, and then we want to define the integral of omega. Well, this is going to amount to taking our connection V nabla to be equal to y plus 2, take OX plus 2 in this case, d minus. Okay, and then we're going to take our function f to be just projection onto the second coordinate. So I guess actually, sorry, these should be x's. And yeah, sorry, actually these should be cube of x's. Okay. So this is projection on the second coordinate. And well, the fact that we want our starting point to be B is just going to correspond to the fact that let's B bar, take B bar to be the reduction of B mod P. So we want common section Sx, at the S of B bar. When you evaluate it at the point B, you get a 0 here. Okay. Well, if you remember what Jennifer did in her lectures, recall that the thing which came up was that you could compute common integrals if you took a full basis of Durand cohomology. So remember we took omega 1, omega 2g. Yeah. Oh, yes, sorry, you're absolutely right. Thank you. Yeah, so it's, yeah, you're right. Thanks. Brilliant. Yes. Omega 1 to omega 2g will be a basis of Durand cohomology. So for this, we just kind of need this actually to be a basis given by any overconvergent differentials on the tube of y. But usually, we actually have a lift of y to some affine open inside our lift of x, and then we take algebraic differentials. For this theory, that doesn't matter. And then we take this big connection. So remember, we actually rather than computing this one integral, what Jennifer did was she computed all these integrals in one fell swoop. And since this is a basis, then there exists lambda I such that, omega is some I lambda I. And this kind of computing all of these integrals in one fell swoop amounts to replacing this little connection with a big connection of rank 2g plus 1. I'm going to call E1 nabla 1, so this will be very important. It will be given by O g plus y to 2g plus 1 d minus 0. Maybe I'm just going to write this more compactly, actually. I'm just going to use a kind of vector notation for this block matrix. So this is actually a length 2G column vector. Is the notation clear? Yep. Okay, great. Okay, and I guess I'm just erasing what I was about to say. I'll just keep it for a second, but then we have a surjection of connections. So then surjects onto our original connection, the nabla. And so functoriality in our theorem, so that was axiom 2. So 2 implies that our computation of omega z is uniquely determined by computing Coleman sections on Coleman sections on of E1. And why does this turn out to be better? It's because when we work with this larger connection, we can use the Frobenius invariance condition. So, well, I mean, we can also use that on here, but it's less useful. We'll see. So what does Frobenius invariance say? So for any, let's say for any point on the tube of Y, we have a Coleman section, which I'm going to write like this. Of E1 nabla 1. Okay. On the other hand, Frobenius invariance implies that when we take this Coleman section, then oh, sorry, yeah, well, sorry, maybe I'll say something else first. Then we also have Coleman section. This is without having used the Frobenius invariance, just saying that Coleman sections exist without any unicity. So we have another rank 2G plus 1 connection on Coleman section of the pullback. And then this Frobenius invariance condition, so 3, implies, if I've got the formulas right, that when I take this thing here, so by what I was saying, I can think of this as a section of the pullback of my vector bundle V nabla, sorry, E1 nabla 1. And axiom 3 is saying that this actually defines a Coleman section, which amounts to this being equal to this. So what does this say concretely? We've just reduced for the identity we had before. Yeah. Yes, sorry, you're right. So I said that this was I guess I should have said that it was. You go back. So I took this to be a global differential, and I guess I should have said that I wanted omega I to be a basis of global differentials. But yeah, so so let's assume this. So if it's not quite true that it's like this, then there's still a map, but the map is slightly different. So without the FIs, the map will be given by something like basically one sense. Is it the other way around? This is probably the other one. Yeah, anyway, something like that. And oh no, sorry, I know. This should be under here. And then if there's some FIs, then you have to do it. Something like that. Technically, with my notation, these are conventional row vectors, not column vectors. Okay, so if you remember, this actually didn't, that's condition 3, but we've used condition 3 now. That's all we're going to get from it. This wasn't the thing that Jennifer used to actually compute the common integrals. So we had an identity, phi star of omega is equal to m times omega plus df, where these f are now some overconvergent functions. So that means that we can use functoriality of connections again, because then this gives us an isomorphism of unipotent of convergent isocrystals. So just unpacking the definitions, this is given by f is equal to 1 Fm. So then functoriality of connections. So I guess it was condition 2 in Besser's theorem. Implies we get an identity of matrices. Maybe I'll write over here, actually. Yeah, just right. Like this. So that was the identity we had before. And so then we put those two things together. That's implied that we're uniquely determined. So this kind of axiomatic approach of Besser, which again, so he called it in his original paper on the subject the Tanakian approach, and that's because he's really thinking of it again as a morphism of functors. It's just a kind of a repackaging in a way of previous results of Coleman, but I mean it's quite useful when you're working in the iterated sense. So This was in the one unipotent or abelian context, but a very similar calculation goes on for arbitrary degree unipotents. Yeah. So I define a Coleman function. So this integral, this function z goes to bz omega is an example of a Coleman function. So any Coleman function is a. So this thing here. So yeah. So I took this was the Coleman function associated to V nabla and F, where I took my Coleman section to be the unique section with this value. Yes. So if you think of the before when we defined iterated integrals in the complex or formal setting, we took a horizontal section of a vector bundle and then we just took a coefficient basically. Took a matrix coefficient of it or vector coefficient, and this function is playing the role of the coefficient. But I mean, one reason to phrase it in this way is some. Actually, in calculations, it's easier, even though maybe it doesn't sound like it, to just work with the vector bundle with connection. So in the remaining time in this lecture, I want to kind of briefly ask two questions. Or maybe, let's say I want to make two remarks. So this thing F has a name. I mean, this, so an ISO, so for any unipotent overconvergent isocrystal, will it be nabla? An isomorphism F from V nabla Frobenius pullback is, I think technically it's the inverse. It's not so important. So the fact that they are isomorphic, so the inverse of this one, it's called a Frobenius structure. Or V nabla. And if you think about it, really, the Frobenius structure was the thing we needed. That was why we were able to kind of do this identity here. So a UOI with a Frobenius structure, F structure is called an F isocrystal. And so actually, really, as I'll kind of explain a bit now and in the last lecture, actually, we could forget about this whole, this whole definition of Coleman sections and Coleman integrals and Coleman functions. We could actually just think about unipotent F isocrystals. Because what we used was the fact, so our original V nabla didn't admit a Frobenius structure in general. In fact, it would only admit a Frobenius structure if omega was a differential whose class in cohomology was an eigenvector for Frobenius. Can happen, but usually it won't. But what we used was the fact that this isocrystal which didn't admit a Frobenius structure was a quotient of a bigger one which did. And the beauty of the theory of unipotent isocrystals is this always happens. There's always some bigger unipotent isocrystal where you have this Frobenius structure. So then the second remark is what is E1? It kind of slightly, I mean, you'd seen it before in a different language in Jennifer's lectures, so maybe it seemed familiar, but really we kind of slightly, that was a real kind of pulling a rabbit out of the hat moment in a way, because it seems to depend on lots of choices. But actually, this E1, nabla one is an extremely canonical thing. So If we take our point B again, and so maybe let's introduce some notation. So sorry for introducing yet more notation, but I think it slightly simplifies making some definitions. So silly notation, so a pointed, you can also do this for connections, but at the moment we're just thinking about isocrystal. So actually soon we'll want to think about connections. It's just a pair. So we'll fix some point B in Y. So a pointed unipotent isocrystal is a pair V nabla and V. So where this is just an isocrystal, and all we've done with this pointed business is something that seems completely trivial. We've just picked an element of the fiber of that V. It doesn't seem very interesting, but fiber B of V. So example, take our E1 nabla one and just take the point 1, 0. And again, maybe that seems like a choice. Why did we take this one? But actually, this is really, in a very strong sense, a very canonical object. So let me define that now. So maybe you can leave this as an exercise, which is very similar to what we did here. So I didn't entirely do it. For any pointed, so it could be an isocrystal or a connection, V nabla V, such that V is an extension of a trivial connection by itself. So that's called one unipotent. This is so for example, that was the V that I just erased, the one which was defining the common integral of omega. So for any V nabla V with this property, there exists a unique map of UOIs or connections E1 nabla 1 to V nabla such that in the fiber at B, fiber at B, and apply this to what I was calling 1, 0. That's equal to V. So that's saying that E1 nabla 1 satisfies, together with this particular point in the fiber, element of the fiber, satisfies this universal property. And actually that tells you, if you think about it, that this pointed connection, E1 nabla 1, 1, 0, is kind of unique up to unique isomorphism, just by applying the universal. Okay. So in fact, now we can make a definition for any n. define n unipotent pointed connection. The n unipotent doesn't really have anything to do with the point. But, so again, it's just has this filtration, this n-step filtration where the graded pieces are trivial connections. So we could also write this as that we're saying that we have a short exact sequence. So trivial. We could write that as O. I don't know, MB to something which is n minus 1 unipotent. An inductive definition. And then it turns out that again, there's an analogous object. There, so a pointed n unipotent connection, which has the following universal property. There's a unique map of connections which sends En to V. Let's see. So maybe I'll give an example. But actually, I'm going to, yeah, no, I'll give it here. Yeah. So it could be, I suppose it could be any rank. So this is an M. Yeah, sorry. So this could be any. So for example, for one unipotent, this was 2G for E1. And then this is something which is n minus 1 unipotent. No, so it's n minus 1 unipotent. So this is just it, sorry, this is an inductive. So we defined 1 unipotent here. And then 2 unipotent is an extension of something 1 unipotent by something trivial. Well, it depends. I mean, it could be any rank. It's just like has a filtration whose graded are direct sums of copies of O. But you could, the summons could be anything. So I think actually I wanted to give an example, but maybe because then I want to keep talking about the example, I'll actually give the example at the start of the next lecture. So I want to tell you one more property, or maybe just a couple more properties about these universal things. So these are, I mean, the definition is rather abstract. And actually the simplest way to prove this lemma is actually also quite abstract. So the simplest proof of this is just to, I mean, maybe I won't even write down because it's not quite the approach we're taking in the course, is to observe that the category of unipotent overconvergent isocrystals, for example, is equivalent to the category of representations of a nilpotent Lie algebra. So representations of a nilpotent Lie algebra are the same as modules under the universal enveloping algebra. And then you just take this En to be some quotient of the universal enveloping algebra, and it's just completely formal. property is satisfied. So that is in some sense the simplest proof of why that's true and why it's actually not even a complicated statement. But maybe if you wanted to actually compute what this connection was, which is what, well, we'll compute some quotient of it at the start of the next lecture, that's not so useful. So we'll give an example next time. And in the notes, actually, there's some more, which I haven't uploaded yet. There's some more examples of exercises where you can compute universal connections. Maybe I'll mention an example. So we were doing this definition. Yeah, so maybe let's say we do this for y. You can actually show that the theorem of Kim that so we take our basis again, omega 1 up to 2 omega 2g. So now take a free associative algebra on n generators. So this QP. This is sorry, that's probably not such good notation. That's but A be a free associative algebra on T1 up to T2G. So an element of A, so basis of A is just given by any word in these symbols. And then A has a natural two-sided ideal, which is the augmentation ideal. So that's just the ideal generated by T1 up to T2G. Okay, and then En is just given by you take this ideal A modulo In plus 1. So that's just a QP vector space, and then you tensor it with O of Y. And then what's nabla N? So I can describe it on some element of my algebra here, tensored with some function, so we can just actually tensor it with 1. It's defined by the fact that nabla N of V tensor 1 is equal to minus the sum 1 to 2g of Ti times V tensor omega I. So for example, if you do this when n equals 1, you'll see that we actually just recover this definition of E1 we had before. So if you do this with P1 minus 3 points, then you get something which is called the KZ equation, which has come up in other contexts in theoretical physics and things like that. So that tells you what it is on affine curves, and then we'll give an example of a projective curve where you can calculate it. And then after that, we're going to say that actually we never really cared about the Coleman functions at all. And we'll explain how to get to Galois representations and do some things with those. Thanks. Oh, wait, is it time to finish? Yeah.
Any questions, comments?
Mm-hmm. Mm-hmm. Yeah. So yeah, I mean, so in Better's formulation, he works over QP bar, but it was just because I didn't, we didn't need that. Yeah. Yeah. QP bar, yes. I mean, you have new residue disks, and then you have obviously more points on the residue disk when you're over QP bar. Yes, I mean, same definition. Well, actually, so, but yeah, so I mean, Besser, so when you work over an extension of QP, Besser kind of slightly redefines his Frobenius map. He does something slightly different from what Coleman does, where he just takes a power. Well, what people usually do, where you just take a power Frobenius so that it's your Frobenius pullback is the lift of it is k-linear. Yes. Oh, the definitions agree, yeah.
Any more questions?
Mm-hmm. Mm-hmm. Yes, absolutely. Yeah. So, I mean, maybe if people don't mind, maybe I'll just give a quick example of, so what does a horizontal section of this connection look like? So it's a sum over all words of length less than or equal to n, some word in T1 up to Tn times some function, that word. And what does it satisfy? So maybe let's just, to simplify things, let's just take our word to be, well, we could just to give an example, let's just take it to be Tn up to T1. That's just, oh, sorry, I guess T2G up to T1, for example. Then, so what's the horizontal condition is saying that, so then F, we want this to satisfy that D of T2G to T1 should be equal to, if we unravel this definition, it's just saying that it's equal to omega 2G plus 1 times F of the word Tn minus 1, T1. And more generally, it's saying that, so I guess I've removed this F here, so maybe let's call it F of the word T2G T1. So D of this function of this F is omega of this, and more generally, D of F Ti up to T1 is equal to omega I times F of Ti minus 1 up to 1. So actually, maybe a better notation would be to say that call Fi, this function which I'm writing is this thing, and then we've just obtained the differential equations dFi equals omega I Fi minus 1. So it's exactly the iterated integral equation. Sorry, that was a slightly wordy way of explaining. So in particular, actually, if you think about it, the horizontal sections of this bundle, they contain all the iterated integrals, length at most n. So it's just a very convenient language for packaging things.
Any more questions?
That they define a ring? Yeah, so I guess I didn't say this, so I definitely would have if I'd taken more of a Tanakian approach, but for example, you can define the tensor product of connections. Which on vector bundles is just taking the tensor product, and then if you have a section S1 and a section S2, then you can show that S1 tensor S2 is a section. That gives you a product. You take the direct, something like that.
Any more questions, comments? In that case, let's thank the speaker once again.